The title of these lectures is Least Symmetries in General Relativity. And last time we stopped at the point where we're discussing the Einstein field equations. Okay, yeah, this 32. Okay, so I'll write them on the board, and then maybe I'll repeat what I said last time, and then discuss their some of the solutions. Okay, so the Einstein field equations, we denoted them by EFEs, maybe, and we wrote them as RAB minus half DAB R is equal to some constant, and we say that we will call that as kappa, and then TAB. And the sum of, so yeah. Okay. So let me repeat what I said about these equations, because they're the basic equations, they're the core equations for these lectures. I said the left-hand side represents geometry, and right-hand side is the physics. Okay, so the information about the geometric information about the manifold, its curvature, and other properties related to the curvature. For example, we saw that this term RAB is the Ricci tensor that we derived from the Riemann curvature tensor. This GAB is the metric tensor, the basic tensor of this theory. R is the Ricci scalar that was defined as the trace of the Ricci tensor. So the left-hand side represents geometry. Some people say it's mathematics on the left-hand side and physics on the right-hand side. It's physics because TAB, that we call as the stress energy momentum tensor. It contains all the information about the matter contained in that space that we are studying. So the distribution and motion of matter, all the information about the distribution and motion of matter is on this right-hand side. So people have discussed this in philosophical sense also, this imagination on left-hand side and the real world on the right-hand side. So all mathematics over there and physics over there. So and I talked about some types of this energy momentum tensor, which sometimes people call as the matter tensor, because it contains all the information about matter. So, for example, whether it's, first of all, it can be vacuum also. If it is zero, there's no matter, it's vacuum. And if it's not vacuum, then there are different types. We can have ideal fluid, perfect fluid. We can have dust, pressureless gas. We can have, for example, the matter can be neutral or charged. If it is charged, whether it's electrically charged or magnetically charged, or there's some other types of charges also defined in physics. So the information come over here. And I said it's not only the distribution of matter, it's the motion of matter also. Because the full name is stress energy momentum tensor. It's contains information about the motion. So whether it's moving, if it's moving, what type of motion it is? I mean, it's only rotation, a spin, or it's moving in some radial direction. And if it is moving, and when it is moving, whether it's with uniform velocity or acceleration, and so all types of possibilities. I wrote you these equations I told you these equations were written in 1915, and for more that's about 107 years ago. And even today, people are solving these. And I told you about the reference books, which serve as the catalogs of the solutions of Einstein equations. So thousands of solutions mentioned. So even as we speak today, people are trying to solve these. And all those techniques, we saw last time that these are actually 10 PDEs in 4 dimensions. So in these lectures, we'll talk mostly about 4 dimensions, although I told you that people solve it in higher dimensions and in lower dimensions also. So 3 or 2, they are called lower dimensions, but I will be restricting myself only to the 4-dimensional manifolds. So, okay. So all those techniques that have been developed for solving PDs, people have used them to solve this system, this highly nonlinear system of solutions. And I think we mentioned that what do we mean by the solution of these equations? By the solution, we mean that we are interested in finding out the square of the line element. And it's in most general Riemannian terms, this is called the Riemannian metric. This is written as GAP, DXA, DXP. And this we defined last time is the metric tensor, symmetric metric tensor, which measures the distance on the manifold. So by solution, we mean that we want to find this line element. So mathematicians mostly call it a metric or a line element. Physicists call it a solution or sometimes the universe and so on, depending upon the physical interpretation of this metric. So there are different names for this. So by solution, we mean that we want to find some, some line element that satisfies this. And today we will discuss some of the solutions. And before discussing that, I want to discuss the trivial solution that we discussed last time, which is called which is the solution for the flat space, the Minkowski. And if we use this signature, last time we discussed we can have 2 types of signatures for these Lorentzian manifolds. But if we use this signature and coordinates as T, X, Y, and Z. So in Cartesian coordinates, we can write this as dx squared minus dy squared minus dz squared. So this is the basic solution in Lorentzian on Lorentzian manifolds in Cartesian coordinates. I also mentioned that in the first term on the right-hand side, sometime for physical reasons, we put a c square also. And I told you that this makes the dimensions of all the terms the same. They are not in the units of length. So c is the speed of light. So if time is multiplied by a constant speed, that constant speed we usually take as the speed of light in general relativity. So this, and I also told you that some people write this CP, some of the books that I mentioned in the beginning, CP as a capital T, which makes this as T squared. So depends on the notation. But I also want to write it in spherical polar coordinate because those are the coordinates that we will be mostly using when we study the solutions of these equations. So spherical polar coordinates are T, R, theta, and phi. So this is ds squared is equal to, again, c squared dt squared minus dr squared minus theta r squared d theta squared and r squared n squared theta. So this is the flat space, the Minkowski. So the solution is called, this is Minkowski manifold. This is the solution for a special case of general relativity that we call as special relativity, the flat space solution. Okay, so from here one thing is obvious, that the Riemannian property that the metric should be positive definite is no longer true here. The metric can be, may not be positive. So we can have Actually, there are three possibilities here for this ds square. It can be positive or equal to 0 or less than 0. So depending on these possibilities, we define three types of vectors on this space, and they are called the time-like when it's positive, light-like or null. Null because ds square is 0. And light-like, they're called light-like because in that case they represent the motion of light particles, photons. And when it's less than 0, they're called space-like. So even from the signature, it is obvious that we will have these possibilities now. I think this is what needs to be said about these basic fundamental things. And now I will like to discuss some of the first solutions that were presented after these equations were written. And let me share the screen and show you. Okay, so this is all the discussion I would try to write in this PDF file, which is still developing. I'm developing these, hopefully, and I will make this available for anybody who's interested. Okay, so this solution, the equations were written in 1915, and the first solution is called the Schwarzschild solution. It was given in 1916 by Karl Schwarzschild. I think I should write it on the board because I like to discuss some of its properties here. Okay, so it's Karl Schwarzschild in 1916. He gave this first solution, and it in the signature that we have selected, it's 1 minus 2m over r dt square minus dr square 1 minus 2m over r square minus r square d theta square minus r square sine square theta d phi square. I think I should mention this small, I should make this small historical comment also, that almost all the books call it as a Schwarzschild solution, but this solution, the same solution was given by another person that was young man at the time, whose name was Droste. So some people say that we should not give all the credit only to Schwarzschild. We should say that it's a Droste-Schwarzschild solution. And actually, about 10 years ago, somebody wrote a historical note in a very important journal of this field, the General Relativity and Gravitation. So Droste actually wrote his PhD thesis on this. I think the title was Einstein field equations, and he presented the same solutions there. And Schwarzschild was a senior astronomer at that time, but mostly books give this credit only to Schwarzschild. I think they should be given both of them. Okay, anyway. So here, it's a vacuum solution. Vacuum solution means the right-hand side of the field equation is 0. Okay, so M represents the mass of the source. Mass of the source. Okay, so any source. I mean, we can start from a planet to a star or whatever. We can take any object or anything that has some mass concentrated at the center of the geometry, like in classical mechanics. And that mass is represented by M. Oh, okay. So the solution actually it uses all those tensors that defined in the last lecture. I will not go into the derivation because that is not the main emphasis here. It's the derivation is given in many books. So basically, I last time mentioned the Bianchi's first identity and Bianchi's second identity. For using those identities, and we calculate all the components of the Riemann curvature tensor that we discussed last time, and then the Ricci tensor and the Ricci scalar. This. And because when there is a vacuum on the right hand side, this field equation actually reduces only to this simple looking equation. It is simple looking, but actually it's not simple because the Ricci tensor involves all the metric tensor, its inverses, their derivatives and products and so on. So it's a highly nonlinear equation actually. And I told you that in 4 dimensions, these are actually 10 equations. But in this case, only we get 4 non-zero components. So a diagonal Ricci tensor, which has given us a diagonal solution. So it's a diagonal solution. Only 4 entries on for the metric tensor, no other terms. And this also involves apart from the field equations, this also involves we discussed about the Christoffel symbols also last time. So the solution, in fact, the integration involves a constant d. And how we interpret that constant d to be the mass, actually, when we take the weak field limit of the source, the Newtonian limit, for the geodesic equations. So the geodesic equation, let me write it. This is the Christoffel symbol we discussed last time, A, B, C. So dot, sorry, it's not ds square. This is the F double dot. The equivalent of acceleration in Newtonian mechanics. So second derivative, but this derivative is with respect to the arc length s. So I think I mentioned this last time also. X dot b, for example, means dx by dxp by ds. So derivative with respect to the arc length parameter s. So this is the second. Actually, this is also the equivalent of equation of motion in Newtonian physics, what we call as the equation of motion. So apart from solving these field equations, this actually the analysis is accompanied by this solving these geodesic equations also. And in this case, we will have 4 geodesic equations for t, r, theta, and phi. And these geodesic equations actually help us to interpret the constant of integration to be the mass of the source when we take the weak field limit. Okay. Some properties of this solution, because this was the first basic solution that was given for these equations. You can see that this solution behaves, this has a very odd behavior when, for example, r is equal to 2m. For example, we cannot take r equal to 2m here. So these are the singularities. R equal to 2m. Another singularity from the first term is obvious, and that is r equal to 0. So the two singularities r equal to 0 and r equal to 2m. It turns out that we cannot remove this singularity r equal to 0, whatever we do. And that is why this is called essential singularity. When I say whatever we do means the first thing we can do is transform the coordinates. Okay. And it turns out that we can transform this line element, this metric, into some coordinates which remove this singularity, r equal to 2m. So that is why it's called removable singularity. Removable singularity. So it can be removed. So this is called so there are different names of this, called the coordinate singularity, and this is called the singularity of the physics, which means something very important physically, which some people realize at that time, but some people refuse to admit what this represents. And they say that even Einstein refused to admit that this essential singularity represents a part of the space-time where the phenomena become highly, unphysical, exotic, and so on, which people did not want to talk about in 1916, about this singularity. So I often say that the success of mathematics when it is applied to the real world situations, to astrophysics, to cosmology, to astronomy, that initially for some decades people did not admit that the physical singularity it is representing actually correspond to something physical in the outer space of the universe. About 40, 50 years. After that, some people started realizing that it actually represents an object which behaves, which has a very odd behavior, a behavior which was not known before that by anyone. And among those were John Wheeler, whom I mentioned last time. And he gave the name of this situation. He was the first person to call this as a black hole. In 60s. So he called this black hole, but even at that time, most of the people did not admit that this is some physical reality. They thought this only a mathematical situation arising in the manifold over there. And we hear the stories of even people like Stephen Hawking and Kip Thorne having a bet on the objects, whether black holes exist or they don't exist, and so on and so forth. And but now we know that it's a reality. And the last three Nobel Prizes have been given. The last year also it was given for people working in this area. Last one was given to Roger Penrose, the mathematician. It's a debate, some say. The second mathematician to be given the Nobel Prize in Physics, they consider first to be John Nash. But then, of course, it's not easy to define who is a mathematician and who is a physicist. And so some people say there are more mathematicians also. Let's not go into that debate, but the important thing over here is that now it's a reality. The existence of black holes is confirmed not only by the merger that was observed in 2014, 13 or the gravitational waves. That was the first confirmation of the existence of black holes. And after 1 year, other objects that we discussed last time, the merger of neutron stars was also confirmed. And I mentioned last time that neutron stars, the properties cannot be studied without studying these field equations and general relativity. So they basically, these objects arise, they can only be defined in mathematically in this theory. Or as Chandrasekhar, I think I mentioned last time, Chandrasekhar said that about the black hole, they're the simplest objects, and the only thing that we need for their construction is some ideas from mathematics. Okay, so you see that this is an essential singularity which cannot be removed, and this is a removable singularity, and there are some coordinate systems where this is possible to remove the singularity. I will not go to those. They are Eddington-Finkelstein coordinates and Kruskal-Cephirus and so on. But that will take us away from the main topic of this. But just to emphasize that these solutions actually represent physical objects, and they're not just mathematical solutions. Another the strange thing happens here when we see, okay, we studied R equal to 2m. By the way, when we say that we cannot remove this singularity, so how will it be confirmed mathematically that whether we can? It's not possible to remove. If some person, some scientist, mathematician is not able to remove this, does not mean that's not possible to remove this. So that is actually confirmed by some other scalars. First scalar we discussed last time is the Ricci scalar. That was the trace of the Ricci tensor. But if we construct higher scalars, then the product of those is called quadratic scalars and cubic scalars and quartic scalars. And if all those scalars are not defined at this singularity, then that confirms mathematically that this is an essential singularity. So those are called curvature singularities. So that is the ultimate test of seeing whether a singularity is essential singularity or not. So we construct the curvatures, the scalar curvatures, and all those curvature scalars blow up at this point. Yes. So okay, so it's R equal to 2m, but this R equal to 2m actually divides the space into two parts. For example, if this R is on this and T, so this is for the TR sector. If I am taking only the first two terms, the TR sector, and this point is R equal to 2m, then in this solution, you can see that this is a region where R is greater than 2m, and this is the region where R is less than 2m. So something very peculiar happens when R is greater than 2m. So when R is greater than 2m, okay, this will remain the same, no change. But when R is less than 2m, you see the sign will change. The first term which was positive will become negative, and this which is negative will become positive. Okay. So the signature that we earlier defined positive for the time coordinate. As I mentioned earlier, we can always write c square over here. But I also mentioned that we mostly ignore it and we call these as the geometrical units when we put this equal to 1. So it's not very good. So at I less than 2m, the first two terms change their behavior. So time becomes distance and distance becomes times. And this I think mentioned last time also, that they're always interconvertible in relativity, because that the c that we multiply with that is a constant of nature. Okay. So if we this was a rectangular diagram for this solution. situation, this situation to represent this situation. The other way to represent it, and that is what Chandrasekhar emphasizes in his book that I mentioned last time. Actually, at the beginning of the lecture, I mentioned some of the books that I've used for these lectures. So I'm referring to those books most of the time. We can describe this situation as r equal to 0 at something at the center of a circle, r equal to m. It's a circle if we consider only the first two terms, but actually it's a surface if we consider the space-time, the whole space-time. So it's the 3-dimensional analog can be like a football with a center. So football is a surface, and this is a very important surface for this object that we call black hole. This is the event horizon. This is the event horizon, and r equal to 0 is called, another name is the true singularity. So there are different names for this point. So it's called event horizon because the information from outside cannot go inside, and the information from inside cannot. So it's like an information. So perhaps this is why Chandrasekhar says that black holes are the simplest objects in this universe. We need only a surface, a point covered by a surface. And how is this obtained? You can see that this second term, which we represent by G22, this is G11. Last time maybe I should mention it again, that this is the metric tensor, and this is G00, G01, and so on, G11, G10, G11, so on. There will be G22 and G33. And so these will be 16 terms, and I mentioned that there will be 10 independent terms because it's a symmetric tensor. But in this case, we only have diagonal entries. G01 is 0 and G10 is 0. So this is G11 or GRR. Some books write it as GRR or G11. And if we take its inverse, and last time we defined the inverse of the metric tensor, how we take the inverse. So this is important for more important for the solution that we'll discuss later. If we take its inverse and put it equal to 0. So note that this will put this equal to 0, and this gives us r equal to 2m. This is a linear equation, it's simple, but for the solution that we'll discuss later, it will be a quadratic equation. I think for this solution, that is all I want to discuss. And there's some question. This lecture available on YouTube. Yes, the notes I know they will be available. Okay. So this is all the analysis, and this 2g over c square are coming here. And I mentioned this last time that there are g over c square. And I mentioned that we can, in mathematical analysis, we can ignore them in some units, and these units are called gravitational units or geometrical units. Okay. Yes, this r equal to 2m is also called the Schwarzschild radius. And some books represent this as RS, Schwarzschild radius. And its importance is that if anything, so you know, you can see that every object has some Schwarzschild radius. take the value of its mass, the Newton's gravitational constant, the speed of light squared, and you will get the Schwarzschild radius. This is an amazing result actually. Why? Because if you put up the mass of the sun, you'll get the Schwarzschild radius of the sun. And which will tell you that after beyond that radius, the sun will convert into a black hole. And if we actually put the mass of the sun, it comes out about a couple of centimeters. I don't remember exactly. 2 centimeters or something like that. So if we can compress our sun into an object of radius of a couple of centimeters, that will turn into a. And same can be said about the Earth also. For Earth, this is a few millimeters, less than 1 centimeter. And similarly, perhaps, I have a Schwarzschild radius and you have Schwarzschild radius and everything. So every object, if it's compressed beyond this radius, which is called 2m, it's converted into this bizarre object, which is called black hole. Okay. Yes, so this is the situation. This is called null radial direction. I mentioned this point, but not in this way. Null radial direction means that you take ds square equal to 0. Null direction, I defined that here. Null direction means ds square equal to 0, d theta equal to 0, d phi equal to 0. These are 0, and only first two terms will be left, and from that you can define this dr by dt, and this will give you this picture when r is greater than 2m, r is less than 2m, and so on and so forth. Okay, then I will go on to the next basic equation with the basic solution, which is actually a generalization of this solution. You can see that there is, apart from mass, immediately after this first solution by Karl Schwarzschild, people started working on the charge generalization within a couple of years by different people. One of them was Reisner, the other was Nordstrom, and there are some people who came up with this charge generalization. So charge generalization means that apart from mass, so this is what sometimes called the one parameter solution of the field equation. But the only parameter here is the mass of the object. And the two parameter solution, the Reisner Nordstrom. So this is 1 minus, I think I should go on stop sharing this screen so that. Okay. So this is the G00 component or the GTT component of the metric tensor. The second component is the same factor, but in the denominator. Square minus r squared d theta square minus r squared sine squared theta d phi square. So you see that this is now for an object which has mass m and charge q. So it's two parameters. So this number of parameters is important for a theorem, which some people think that it's a conjecture. I will mention it So the number of parameters. Okay. So you see again, we can discuss the singularities. R equal to 0 is again an essential singularity. A point like singularity, the center of the object. But for other singularities, for coordinate singularities, I told you that we take the inverse of GRR and put that equal to 0. So this, take this inverse and put it equal to 0 minus 2m over r minus q square over r square equal to 0. And now you can see that this gives us a quadratic equation. And it will have two solutions. Is it correct?
Yes,
It's okay. It's okay. Huh?
I think plus q square.
No. It's okay. Mhm. Oh, that's I mean, this should be plus here, huh? No, actually, we done a mistake over here. This is plus. Is it okay now? And I think the same mistake I've done in my notes also. Let me see. Then I need to correct it. Yes, this should be plus over here because I know the event horizon equation is correct. So the metric I have not. So there's a typo I will correct in the note. This should be plus over here and plus over here. And these are the two. So one first we can call as R plus and the second as R minus. So now in this case, you see there are two event horizons. And one is greater than the other. R plus obviously is greater than R minus. Okay. So the greater one is called the outer event horizon. Is the outer horizon. And this is the inner horizon. So if we draw circles as we did earlier, if this represents r equal to 0, then the first circle will represent r minus, and the second circle will represent, or actually these are surfaces. In 2 dimensions it's a circle, but in the 4-dimension Lorentzian manifold, actually they are the surfaces. And if we draw the TR sector, so this part is called TR sector when we ignore the other two coordinates and only take the first two terms. So there will be a point where r is equal to r minus, and then there not point, actually region, where r is equal to r plus, and this is the region where r is greater than r plus, and this is the region where r is less than r minus. and so on. And this is R0. So this is an interesting mathematical generalization, although the astronomers and physicists are not convinced that there are many objects in this universe that are actually electrically charged. So this also I mentioned that Q is the electric charge. And in order to incorporate electric charge, of course, you know that we need the electromagnetic potential also. So this is actually a solution of Einstein field equations combined with Maxwell equations. So this is what are called the Einstein-Maxwell field equations. So this represents gravity plus electromagnetism. And electromagnetism is represented by the Maxwell field tensor. So this this is an object which is electrically charged. I'll briefly talk about an object which has magnetic charge also, but for mathematicians, they are just the addition of parameters. And as I said, the observational astronomers, astrophysicists, they're not convinced that they're charged black holes. Even if they're charged black holes is formed, they shed their charge very quickly, immediately after their formation. So far, nobody has seen any electrically charged. Okay, so these are this is the analysis for this. The only difference is that it has two parameters. It has two regions. This is the region between these two horizons. And is there anything else we like to mention? Yes, one thing. Yeah. This in the first case there was that was a linear equation. I mentioned that there was only one solution, but there another situation can arise. I told you that this is the singularity. In the case of this solution, there is one circle. The singularity is always covered by a surface. Here we can have a situation where there are two other situations also. So this is the solution we're talking about when mass is greater than charge. Mathematically, it's an interesting situation. We can have other two, because it's quadratic equation, we can have mass equal to charge or less than charge also. Okay. So these are called the usually not considered discussed in the basic lectures as these lectures, but there's called the extremal situations, or if we want to give it a physical interpretation, they're called extremal black holes. So it's an object without the event horizon, which Roger Penrose called as the naked singularity, and he states a theorem which people think it's a conjecture, not proven yet, that God abhors naked singularities. But naked singularities cannot exist in nature. This is called Roger Penrose's censorship, cosmic censorship conjecture, or cosmic censorship hypothesis, they will say. That we cannot have actual situation, physical situation, where there is a singularity, but it's not covered by horizon. Due to Roger Penrose. We will not, yeah, this is cosmic censorship, I mentioned it. I should mention the name of Roger Penrose also here. is given by this. Okay, any case. So now we quickly like to come to the third major solution that is discussed in all these. So these are the basic solution whenever they discuss field equation, they discuss these three basic solutions. The third solution is the curve solution. It's a bit lengthy solution, but I think I should write in on the board the next at least to. Okay, so the Kerr solution given by Roy Patrick Kerr in 1960s. The mathematician from New Zealand. Presently, I think he is in Italy, Pescara or something. Okay, the Kerr solution. So, in order to use the same parameters, same definitions, this is rho square, EC square minus 4ma. Yeah, this should not be alpha. This is A. AR and square theta over rho square. And now you see for the first time that there is a cross term appearing. Oh, I forgot to. Yeah, but I don't. I want to have a look, or maybe I can buy so that I have both the blackboard as well as my notes. Okay. R square plus A square plus 2mr A square and square theta over rho square and square theta and phi square. And let me erase. So we have another equation of this type. This was Reiser-Armstrong. So just remember that there will be this radical sign square sometimes under this sign, which will give rise to some peculiar situations in case this is negative. Okay. So that is still debatable. Some people say it's physical, some say it's non-physical. That is why it's called conjecture or hypothesis. And people have been working on proving or disproving for many decades since Penrose proposed this. Okay, so the terms I have defined here, A is actually the rotation parameter. It's the angular, it's small m. Okay. The angular momentum per unit mass. So it's called the rotation parameter. So this gives this a new look. I mean, different from the earlier solution. That now they were static. The earlier solutions were static vacuum solutions. Now this is a rotating, a spinning solution. Rho square is equal to r square plus a square cos square theta. And this delta is equal to r square minus 2mr plus a square. So the additional factor is the rotation, and mathematically, whenever there is a rotation in the in the space-time, this will be represented by this product term. So this is an interesting observation. Whenever you see a metric tensor which is not diagonal, and there's a rotation, there's an off-diagonal term, this means that there is some rotation involved. I should have mentioned earlier in the case of Riemann that if you put charge equal to 0, you get the original Schwarzschild solution. So that reduces to the Schwarzschild solution. Similarly here, if we put A equal to 0, this gives us the Schwarzschild solution. And this is actually a theorem, Birkhoff's theorem, that any solution of vacuum field equations will be a static solution given by Schwarzschild. So any solution which is where we have a vacuum and with only the mass one parameter or other, they will reduce to the Schwarzschild solution. So you can see if we put A equal to 0, this will go to the Schwarzschild solution. The first thing after the solution, if they're physical solutions, we discuss event horizons that we have discussed earlier. So the event horizon here will be discussed, will be obtained by putting this equal to 0. I mentioned the inverse of GRR. So this equal to 0 will give us the event horizon equation. Here again, it will be a quadratic equation. And here, this will be m plus minus m square minus a square. Is it correct now? Yeah. So the same situation arises here also. If the magnitude of mass, note that we are comparing mass with the charge and with rotation. We can compare them only because we're taking the constants involved is equal to 1 in gravitational units. You see? So that is why we are able to compare mass with charge and actually the magnitude of the mass and the charge. And this is a dimensionless activity. Again, the angular momentum per unit mass. So if m is greater than a, this is the usual physical situation, called curve. And the observational people believe that most of the objects from black holes in this universe actually correspond to curve, their rotation. This is another question about whether they can get rid of this rotation at a later stage, and when do they get rid of it? So this is another not relevant for this. But mostly they are spinning. So the rotation is actually spin. Okay. So spin along some axis, like the spin in Earth. So there is some axis, and this is a spinning around that axis. This is the rotation. So these are spheres. but this spin makes it an axial symmetric situation. So this axial symmetry, after these notions, I will come to the symmetries and how they are represented by generators and what role do they play in the groups. This axial symmetry, we will talk about later also. And there can be other types of axial symmetric situations. And just to mention, just to emphasize this point, that we can have an axially symmetric situation for an object which is not spherical in shape. I'll give another example also after this. So this is a sphere. It gets axial symmetry because of its spin. You see? So it's important to emphasize. The earlier two objects were spherically symmetric. There were all the symmetries of the sphere, but they were not spinning. So this is a sphere, but it gets its axial symmetry because of these. Now it has some particular favored vector that gives this axial symmetry.
There is a question we want to ask.
Yes, yeah, sure. For those.
Can I ask you,
Yes, yeah.
Mr. Khalid?
Yes.
Thank you for the opportunity. I want to ask you the first question.
Mhm.
What do you think is the biggest weakness of general relativity? And what are the possible ways to solve it? And the second,
Sorry, what is this?
what do you think is the biggest weakness of general relativity?
Weakness.
And,
okay.
yes. And what are the possible ways to solve it? And the second question, how about electromagnetic interaction in the Reissner-Nordstrom case? Thank you very much.
Electromagnetic interaction in?
Reissner-Nordstrom case.
Oh, Reissner-Nordstrom. Okay.
Yes. Thank you.
Okay. Actually, so I will only give you short answers to your questions because actually they lead to the whole new fields and areas where we go beyond general relativity. So general relativity, as we are discussing here, is the classical theory of general relativity where we do not incorporate any quantum effects. And the black holes I am discussing here are the classical black holes. I am discussing only those properties which can be discussed in terms of this classical general relativity. Okay. I will not go into, because that is not the main the focus of this subject. I will not go into the discussion of the black hole where, for example, Stephen Hawking incorporated quantum mechanics, and where black holes do not only absorb things, but they emit things also. They emit radiations, and these radiations are called Hawking radiations. And we arrive at that situation only if we incorporate quantum mechanical effects. Or even if we incorporate the effects which are called the semi-classical effects. Not full quantum mechanics, but semi-classical. So this is the one direction where we can go beyond when we study Hawking radiation, for example. And actually, when I mentioned that the black holes sometimes shed their rotation and shed their charge, I did not want to go into that. They can shed their rotation through this Hawking radiation. So if they radiate, and as Stephen Hawking mentioned in his famous paper, the evaporation of black holes, And he mentioned even in the abstract of that paper that there might be some black holes that have evaporated from this universe. And this evaporation is by means of Hawking radiation. So these effects we get only if we incorporate quantum mechanical effects in the classical relativity, which I will not discuss at all. So this is one direction where we can combine quantum mechanics, and actually that should lead us to a subject which people call quantum gravity, and which actually does not exist today. So there are many approaches to that subject, which is called quantum gravity, where we should be able to combine quantum mechanics with general relativity. But so far we have not succeeded. That's one way. Another direction where we can go beyond general relativity, and I think that's what you want to say, is that we change the basic field equations. Actually, we change the basic Lagrangian, the Einstein-Hilbert Lagrangian, where the Ricci tensor R plays an important role. And those fields, those branches where we take, instead of taking that Ricci scalar, we take higher derivative terms or higher order scalars. They are called higher derivative gravity theories. Again, I will not discuss about those, but they are called alternative gravities and higher order gravities, and higher, and so they're different names. So alternative theories and so on. So, so those are the areas where we can go beyond general relativity. And you said, why would we like to go beyond general relativity? If there are any weaknesses, so that's I mentioned. There are some phenomena like Hawking radiation that cannot be explained merely by classical theory. And why do we go to higher order, higher derivative theories? Is some people think that the presence of dark matter and dark energy and some cosmological questions, which we have not been able to solve if we remain in the arena of general relativity, we might be able to have some ideas about those unsolved problems. So there are plenty of reasons why we should go beyond general relativity and incorporate other effects also. That was I think I've answered your question. That was your.
Electromagnetic interaction.
Oh yeah, electromagnetic interaction. Yes, okay. So the electromagnetic interaction, you mean that some particle comes in the field of the Riemannian gravitational field. Okay. So what is the motion of particles? So the motion of particles, briefly mentioned, is discussed when we solve the geodesic equations for that particular case, which is actually the equation of motion. I mentioned that in general relativity, geodesic equations plays the role of equation of motion. So if we solve this geodesic equation for particles, that gives us the motion of particle in that particular field, whether it's Schwarzschild field or Riemann-Armstrong. Now that particle can be neutral or that can be charged. There can be different situations. So if it's a charged particle, it will give rise a different. So mainly, how do we deal with that? Mainly, we will solve the geodesic equations for different particles. And if you are interested in that, I will refer you to the book by Chandrasekhar that I mentioned in the first lecture. It discusses this subject of motion of particles with black holes in very in detail. Another book is the Black Hole Physics by Frolov and Novikov. Black hole physics that also discusses this in detail. So as our the main focus of this course is the mathematical aspects more than the physical aspects, therefore I have avoided these questions. Maybe we can have that discussion on a different lectures. But this here I am restricting myself more to the mathematical aspects. Okay. Okay, so again here, this should be positive under the square root. If it is not positive, then it gives you peculiar situations. And those are called extremal black holes. And I don't want to go into those situations. Okay. Yes. So the coordinates here that we have used in the Kerr metric, they are called the Boyer-Linguist coordinates, these. I'm mentioning this because the Kerr metric can be written in other coordinates also. But these are similar to the Schwarzschild coordinates, and most of the time when we do an analysis on this Kerr metric, this is in Boyer-Linguist coordinates. Okay. Another factor I should mention that this singularity here, apart from this point singularity r equal to 0, there is, and when we put rho equal to 0, this gives us a singularity at r equal to 0 with theta equal to pi by 2. So this is a different type of singularity from the one that we discussed in the previous two examples. So this is called a ring singularity. So there is a ring at theta equal to pi by 2. And this is the situation, this equation, where I have said that this m should be greater than a in order to avoid the non-extremal case. And here again, there will be r plus and r minus, two inner and outer singularities. Here there is another object also called the ergosphere, which is the region located outside a rotating black hole. So ergosphere I should draw on the blackboard. Okay, so if this is a sphere, then in this Kerr black hole, there is a sphere like this, or there is a region like this also around this spherical object, and you see this region. This region is called an ergosphere. And there are interesting things happen in this region, which do not happen in the previous two black holes, in the Schwarzschild and the Riemann-Armstrong. Here, actually, it is possible to extract energy Yes. So this is the ergosphere. Is ellipsoidal in shape and situation so that the poles of rotating black hole, it touches the event horizon, stretches out to distance that is equal radius of the event horizon. So it goes beyond the event horizon, and this is what I have drawn on the blackboard. Another solution is the Kerr-Newman solution. So Kerr-Newman means this is the Kerr solution with addition of a charge. So we have added charge only to this. So in the Kerr, there was only A, the rotation parameter. In the Kerr-Newman, you can see that there's a Q also appearing here, this Q. So this is the charged Kerr. This is the charged Kerr solution. So rotation plus charge Q. Okay. And obviously, if we put to charge equal to 0, rotation equal to 0, this should reduce to Schwarzschild solution. In the Kerr-Newman, the event horizon equation you can see is long, but again it's quadratic. It's not more complicated. There's only two terms more. Apart from mass, it has charge and rotation. Okay, and its solution is this. It involves a square minus q square. So a square minus q square for the Kerr-Newman. For the Kerr-Newman case. Okay. And again, the same condition if m square is greater than a square plus q square, so that the terms in the radical sign is positive. It's called non-extremal case. And if this is not the situation, then we call it as extremal case. If this becomes negative, it's called extremal case. Okay. And yes, this reduces to Schwarzschild when we put A is equal to 0 and Q is equal to 0. This is the ergosphere for the Kerr-Newman metric, which
There is a question.
But
there is a question.
Oh, okay, yeah.
They're asking about the energy momentum tensor in these cases.
Yes, okay. Yeah. So the energy momentum tensor I've mentioned will come from this. This is the electromagnetic vector potential in 43. So this vector potential actually will give us the Maxwell field tensor. And from that Maxwell field tensor, we will get the energy momentum tensor for this electrically charged situation. So, as I mentioned earlier, in this situation, we will not only solve Einstein equations, but actually we will have Einstein-Maxwell field equation. And this Maxwell tensor comes from this equation 43, which is the electromagnetic potential. So this is the electromagnetic vector potential with only one index over here. This gives us the charge for this body. So the charge comes from, so we discussed two solutions that have charge, Riemannian and Kerr-Newman. In both the cases, we will have this electromagnetic vector potential. Otherwise, if there is no charge, we only have gravitational potential. And gravitational potential is the mass. You see? So when we have only gravitational potential, we have mass. When we have electromagnetic potential, we get electric charge here. So we construct the Maxwell field tensor from this electromagnetic vector potential, and that gives us the stress energy tensor. Or maybe I should include that the exact form of the, I have not included that in my notes. The different forms of stress energy momentum tensor we discussed last time also. So I think this question also motivates me to include one section on that, where I include different forms of electromagnetic, different forms of the energy momentum tensor. So I'll mention, for example, the energy momentum tensor for perfect fluid and for electrically charged object and magnetically charged. So I think I should conclude today's lecture with this theorem, the no-hair theorem. So you see, this was Kerr, and then Kerr-Newman, which I did not write on the board. It is a 3-parameter solution with M, charge, and rotation. 3 parameters. And that leads us to this theorem. It's called the no-hair theorem. I also have. Okay. So the no-hair theorem means the black, this is a simple statement is that black holes can only have these 3 parameters. Okay. And most textbooks give this in the form of a table, I think, which is very useful and interesting. And so far, I have not included in my notes, but I will draw it over here. That if M is the first parameter, Q is the second parameter, and this A is the rotation parameter, then the first solution, Schwarzschild. I think I mentioned he was German astrophysicist, actually, Karl Schwarzschild. In astrophysics, there is a famous textbook by Martin Schwarzschild, who was his son, one introductory book in astrophysics. So in Schwarzschild case, we only have this mass, and we do not have this. The next, Reisner and Armstrong. Or strong, which we usually abbreviate as Rn. So it has mass and charge, but no rotation. Then we go to Kerr. It has mass, no charge, but rotation. And the last we discussed was Kerr-Newman. It has mass, charge, and rotation. We sometimes call it as Km. So this no-hair theorem says that actually some people prefer to call it as a no-hair conjecture and not theorem. And interestingly, I think we'll be able to know more about whether it's a theorem or conjecture in another lecture, which I think is after me in this same room. I think is called the hairy black hole. If I remember correctly, lecture after this. 12. Yeah. This is a hairy black. Hairy. So hairy means those black holes which involve other parameters beyond these three parameters. So, but they are in a different sense. Those, and we'll be able to know more. So this summarizes what we have done so far. And it's important to note, I mean, mathematically, this should be a requirement, that when we put charge in this class, when we put rotation equal to 0, we should get Reisner-Armstrong. If we put charge equal to 0, we should get curve. And if we put both of these equal to 0, we get Schwarzschild. So it's an obvious thing, but I wanted to emphasize that. I think it's a good point to stop here. So if there are any questions, any comments, or as Roger Penrose would say, any objections? Let me see if there are any. Do you see any question more? The only those questions that I've already answered. Huh? Four equations. R0 equal to 0, R11 equal to 0, R22 equal to 0, and R33. You know, in spherical geometries, is a multiple of R22. So in fact, we have three components of the Ricci tensor which are non-zero, and we put them equal to 0 in order to solve the case. So this will be the correct state.
So what about the other cases?
Yeah, in all these cases. I mean, we cannot have Ricci tensor equal to 0. So in all these cases, they are non-zero.
But they are scalar.
And we put them equal. If this is the case of only a gravitational field tensor, we put this equal to 0. And if we have charge involved, then there will be Maxwell field tensor involved, and instead of Einstein field equation, this will become Einstein-Maxwell field.
Like the Einstein field equation to solve this. So like we are already taking the scalar flat that the R is 0, so and it's vacuum solution. So all these solutions are like the scalar flat.
No, they are not. They are not flat in any sense. Otherwise, this general relativity will reduce to Newton theory, the Euclidean space. So they are not flat. Is there anything I should make clarify it? Well, this is what differentiates this subject from Newtonian mechanics, which is actually genuinely flat, where we have Newton's law.
The thing is, everybody agrees that they are not flat.
Yes.
In the sense of Riemann.
Yes.
But in the sense of Ricci, I think some of them are actually flat.
Yes, I mentioned last time that it's possible that a space is Ricci flat, but it's not Riemann flat.
Yes.
But the converse is not, it's not possible.
But some of them are Ricci flat.
Yes, some spaces, yes, we can have it.
They are not flat.
If they are not Riemann flat,
They are not Riemann
yes,
flat.
yeah. This is possible. Yeah. Yes, but Schwarzschild is not. Schwarzschild is not
Scalar flat.
It's Ricci tensor components are not zero.
Yes, but the trace of the Ricci.
I have not given them in these notes, but they can be seen in any textbook. The long expressions. So I did not want to move away from the main subject of this. So how to solve these equations and their physical interpretation. I think I'm already getting. I want to go to the Lie derivative definition, Lie derivative, and how to construct generators and the algebras from them into I'll have to go quickly in the next lecture. But definitely it's not a case of the genuine flat, which we call the Riemann flat. Are there any questions on this?
Unfortunately, they were not able to listen to the conversation.
What? But we are still on Zoom. Huh?
Yes.
Well, then, I think they should be able to.
They don't hear the questions. They don't
Oh,
hear the
so,
answers.
okay, but they have heard my answers. Okay, then thank you very much, and I think I should stop this.